Recitation problem 3. A box of mass equal 10 kg, initially at rest, is being pulled a distance of 10 meters along a rough horizontal surface by a rope that is parallel to the horizontal. The coefficient of kinetic friction between the box and the surface is 0.25. What is the work done by the pulling force if the speed of the box at the end of the 10 meters mark is 5.0 meters per second? First, let's find all the forces acting on the box and then evaluate conceptually the work done by each one of them, particularly those forces which are non-conservative. The main force that is acting on the box, and it is mentioned in the question, is the tension T. There is also the normal force which is acting in a perpendicular form with the surface of contact. There is also the weight mg, which is acting straight down. And finally, the friction force, which is acting in the opposite direction of motion. The tension is doing a positive work because it's acting along the same direction of motion. The normal force is acting in a perpendicular form with the displacement, therefore it does zero work. The friction force is acting in the opposite direction of motion, therefore it does negative work. In general, the work done by all these non-conservative forces, the tension, the normal force, and the friction, is not equal to zero. Therefore, we can use either the work done by the net force equal to the change in kinetic energy, or the work done by the non-conservative forces equal the change in kinetic energy plus the change in potential energy. Personally, I like using the second equation because of its simplicity. The work done by the non-conservative forces comes from the work done by the tension plus the work done by the friction force and the work done by the normal force. Don't include the mg because the weight mg is a conservative force. All of those equal the change in kinetic energy plus the change in potential energy. As mentioned before, the work done by the normal force is equal to zero because it's acting in a perpendicular form with the displacement. Notice also that the change in potential energy is going to equal zero here because the object is not going to change heights. In other words, the height initial and the height final of the object are exactly the same. Now, let's simplify this equation further. Leave the work done by the tension alone. The work done by the friction force, which is a constant force, equal the friction force times the displacement times cosine 180. The friction force always makes an angle of 180 degrees with the displacement, equals the kinetic final minus the kinetic initial. Notice that the kinetic energy initial is equal to zero because the object starts from rest. All is left for us to do now is to find the expression for the friction force Fk. In order to do so, we need to apply Newton's second law to our system. The sum of the forces acting on the box equal to the mass times the acceleration. I'm going to assume the x-axis to point towards the right and the y-axis to point straight up. The forces that are acting on the box are the normal force, the mg, the tension, and the friction force. They all add up to the mass times the acceleration. The x component for this equation is going to give Fn to be 0 because it is vertical. Mg is also acting along the vertical, therefore it's 0. The tension is positive. The Fk is negative, it's acting in the opposite direction of motion, equals mass times acceleration. This equation is not important to us, but the y component is the one that we're going to need. The y component is going to have Fn minus mg. Both of those are acting along the vertical. The tension and the friction force are both equal to 0 because they are acting horizontally. Since there is no acceleration along the vertical, therefore that is going to equal to 0. As a result, we're going to have Fn to equal mg in this case. As we know, the friction force equal to the coefficient of friction mu k times Fn. Substituting Fn by its expression, which is mg, we obtain Fk to equal mu k times mg. Let's now substitute the Fk in our expression that we have obtained earlier using the work done by the non-conservative forces. The result is going to be work done by the tension plus, instead of Fk, we substitute that by mu k mg times the displacement d. We know that the cosine 180 equals -1. That's going to equal the kinetic final is equal to 1/2 mv final squared. Isolating the work done by the tension, we obtain 1/2 mv final squared. When we move the mu k mg d to the opposite side of the equation, it becomes positive. Therefore, positive mu k mg times the displacement d. Solving for the work done by the tension, we obtain 370 joules.